Hello everyone. So today I have another hydraulic mechanics for you guys. So as you can see that this is like what can we call it, like a pipe or um something that this is the water that is flowing inside this kind of thing. So here you can see that this height of this part is equal to the side of this part. But you can see that there's a little thing here that is quite shorter, so it means that this is like a throat of it. So the height, or we can say that the diameter of this kind of thing here, the part here, is shorter than those who are at the ends. So as you can see that if water is going for example, if it's going at a velocity of a, so when it goes to another like the area that is smaller than the first part, it means that the velocity have to be reduced because once it's like pushing like this, so the velocity will be faster. Then we will slower like this again. Okay, so without further ado, let's get started with the question. So they ask you to determine the volume flow rate. And what they have here is it's like the manometer. The manometer that's we have the height difference of the mercury. So we have here and here. We can say that it's the height difference is 6 centimeters, and there's another height difference from the pipe, which is x centimeter. So now we have to assume that it's like the one dimension because it's easier to work on one dimension over 3D, three-dimensional. Okay, so now we have to say that let's assume that it's one dimension and it is a incompressible flow. So when it is an incompressible flow, it means that there have a lot of conditions that we have to, like if it's a compressible flow, normally at this level, it's hard to work on the compressible flow. So that's why we have to assume on the incompressible flow and one dimension. Okay. So after this, we know that the normal equation that we have is this one, right? The initial and the final rate, the area with the velocity, and like the initial when it starts here and the end that is going out here. So after that, we have the equation that we can solve from this one is the pressure over the density plus with the velocity squared over 2. And then we plus g squared, as gz1. Z is the measured the centimeter the length that is measured from the center line. So as you can see that this is a center line, right? So Z is the length that measured from the center line. And then we have the other side of the equation, which is pressure 2 over density plus velocity square, velocity of 2 square over 2, and we plus with the gravity and the another again it's the length measured from the center line. So now we have all the equations that we want. We can from this equation, from this relationship of equation, we can convert it as velocity 1 equals to q over a1, and velocity 2 equals to q over a2. So with this kind of relationship of the equation, oh, it's not that pretty. Okay, with this kind of equation, we can substitute it in the next equation that we're going to have. So now we rearrange all of the pressure with pressure here So we have density that is the same density between the two sides because we have the same type of liquid, which is water. So the density stays the same, and also the mass will stay the same as well. So now we have P1 minus P2, which is the pressure. Again, because it's similar, so don't forget that this is like a little bit curved and this is like straight. So it's pressure and density. And then we have equal to v, which is the velocity, v squared minus v square 1 over 2. And then because since we have all the this one is the same, so we just cancel it out. And then with this relationship, this one is v1, right? We need v1, and this is v2, we need v2. So we can substitute this one into the equation that we're trying to solve. Okay, so it would be 1 over 2 q over a2, and then all of them square minus q or a1, area 1, 2, I mean square, and then everything in the bracket because it always belongs to this part, right? So as you can see that this part here is this part here. Okay, then we have the pressure. Then we have the pressure here over what can we say, density. Okay, so now we have the hydrostatic equation that we're going to solve. So the hydrostatic, okay, let me write it. Hydrostatic equation, which is written based from the center line. So now we have pressure 1 plus the density multiplied by gravity and multiplied by the x, the length of it. Then we have pg, I mean this one, g, and delta h equals to the density here plus with the another side of it, I mean, plus with this one, another density, g and delta h. So after we have this equation, we can solve for it because we have similar things here that it's like in common things, P2 and P1. So now let's go back to P1 plus P2 over the density equals to G, H, and this one over P minus 1. So after this, we can see that the I mean this Q here, the Q here will be equal to 2G H, the delta H, the delta height, density M, the area of each one square, and then we have this one, the density minus 1 here. It's actually this part. So we have this one is the P here, right? And then this one is this one. And then we multiply by the subtraction of area 1 square minus area 2 square. And then we have this part. After that, okay, so let me rewrite it again, clearer. So it's 2G delta H, density, area 1 square, area 2 square, over density minus 1 and the multiple by the area of 1 square by area 2 square. So everything here is actually, this one is actually inside the bracket. Okay, so after we have everything in the square root, we can say that a1 a1 here, so I'll use another color. A1 here equals to pi r square, or we can say that pi d over 2 square. So we have pi d square over 4, which is pi multiplied by the 0. Actually it's 0.5 because centimeter to meter, 0.5252 square over 4, and the a2 is the same thing here, pi d square over 4, which is pi multiplied by 0.03504 square over 4. So now we have 0.000964 meter square. We have delta H equals to 0.06 meter, and density, the equation between density is this one is the density of the mercury, right? And we have multiple by the density of water, but then we have to divide by the density, which is the liquid inside the water. So we have 13.6, the same thing here. So we have this relationship, we have everything. Then what's going on next is to substitute everything inside the main equation. Okay, so now don't forget this part, the root part of it. Oh, so it's 2 with the gravity value and then the delta H, and multiple by this thing here over we have it's actually 1 over the area, 0.000964 square here, and we minus this one, 0.000217 square. Alright, okay, so now after having all of these, we can work it out, and the answer is 0.00416 meter cube. Okay, so this is the volume flow rate. Okay, so on the other hand, we can write it as this as well. It's not only like we can write in this form, so it's actually Q equals to 2G delta H, and it's all of these here over P minus 1 over 1 over A minus 1 over A1 square. Alright, so if we put this one into 1 over A2 square minus 1 over A1 square, we can, it's equal to A1 square minus A2 square over A2 square multiplied by A1 square. So with this one, we have we can say we have it here. We move back to the upper part of the fraction. So now we have this part here, and that's it for the equation. So we can just substitute either way that we find it more easier and more comfortable. So that's all for this one. I will upload the actual neater handwriting in the description box below. Thank you.